or another way, if I wanted to use more names, I could have said arrows between Erisman sites and Grothendieck topoi. Quite extremely messy. So this is in some ways the sequel to Julia's talk, but I'll try to sneak in enough information that people can follow who didn't hear the first half. And so let's first make sure I know how to use this thing. Here, there we go. Left and right. Okay, well, it's only going well for the first slide. So anyway, we are looking at, we really want to have these Erisman sites for Grothendieck topoi, as Julia told us. And the story started with Dalhousie. And for Grothendieck sites, we know that we can represent them by either site-tectonic maps, which have been improved by Compostela and Grothendieck for the two directions. But Lawson and Steinberg came at this from the perspective of inverse semi-groups and pseudo-groups, and were interested more in this ordered groupoid perspective, which Darian and I indeed turned into a double categorical representation. And the only problem was that because these guys are really closely related to those guys, we didn't have categories of fractions, and because there are not enough of them. And so in order to fix that, we tried to go in several different directions. So to answer some of the questions asked at the end of Julia's talk, when we started the question of this project, we were like, well, we know how to do it for étale groupoids. Can we use the étale groupoids to fix things on this side? Because we have groupoids here too. But the problem is that this is the algebraic direction. The étale groupoids are in the geometric direction, and we just couldn't get them to talk to each other. And so we decided, okay, let's just stay on the algebraic direction for now, and we still want to understand the connection with the étale groupoids. And I'm actually hoping that some things that I heard yesterday over lunch might help there eventually. But we need some other fractions for the étale groupoids to make that thing work. So not today. So what we ended up doing instead was to use something that we know about, how to enlarge this part here. And as we were doing that, we realized we don't have to stick with Dalhousie. We can work this for arbitrary Grothendieck topoi. So I am not going to tell the Dalhousie story for the rest today. We'll work with the Grothendieck topoi in general. And so as Julia told us, if we work with left parallel ordered categories with an Erisman topology, then we can get all the Grothendieck topoi, and I want to tell you what we need to do for the arrows. Interesting. This one bit, yes. What we had done originally for the Erisman sites was that we showed actually that we had an equivalence between left-constitutive site or left-constitutive categories and ordered groupoids, and then we just had to translate what covering, preserving, and covering flat meant, which became covering, preserving, obvious thing to expect. Covering flat took a little bit of work, and I will review that in a moment. And then, so we are now going here. Now the problem is, of course, that we do everything in terms of E and M and E, and they are not unrelated to our Grothendieck topology. So we have to be a bit more careful here. But with enough conditions put on, covering preserving will be easy. Covering flat is what is going to take some work. And then I'll quickly say something about lambda comparison and all the other stuff. But that's easy. The covering flat part is the part that we need to do work for today. Quick review of how these things were created. So for Dalhousie, the ordered groupoids have double categories with horizontally isomorphisms, vertically the poset, and we're thinking of the objects as the sub-objects in the original site harmonic maps. And have the property then that for every corner like this, there's a unique cell completing it. And for the top cell, I'm thinking of this as the restriction of the bottom arrow along this inclusion. The result is then that we get a double category with domain discrete variation. So now go to Grothendieck topoi. We get rid of the isomorphism here. We're thinking of these as single arrow coverings in the CM site. And we still have the subobjects sitting here. And we have the extra conditions about left capability that Julia talked about. And topology in both cases is on the vertical arrows, but there's of course conditions on the topology that are depending on the horizontal arrows. So the horizontal arrows give conditions on the topology. So the Arizman topology is not exactly the same as a Grothendieck topology. It's a Grothendieck topology spread out over those vertical categories. So that's this way, yes. So now, what we had in the past was that left-sensitive categories. We had a two junction between them with the ordered triploids, where in this direction we are going by subobjects, which is slightly different from what Miroslav did in his work. When he went from a category with a factorization system to a double category, he just took the same objects, put one class of arrows in the horizontal direction, the other class in the vertical direction. We're kind of doing that, but not exactly the same. So we're using the fact that our right class consists of monics, and we are modeling out by data subjects, basically. And at the very end, I'll make some comments about why that's interesting. But not our idea, by the way, that came from Lawson and Steinberg. So we do the same thing here. And so if we just take the CM sites with all functors, so for the moment I forget about Grothendieck topology and taking functors, then I can make that same two junction with left parallel ordered categories with all double functors. And if I restrict myself to the double categories where the vertical arrow categories have maxima in each component, each component has a maximum, then that junction becomes a Gaussian reference. And that's true for the first case here, and it's true here too. And so that is going to help me then. So for the next slide, yeah. So all I need to do is I need to translate these two conditions. Well, covering preserving, easy to translate. Covering flat, not so easy. But it's the only one that's nasty. If you go on with the lambda comparison, no problem, the rest of it goes the way that you would expect it. It's only for the covering flat that we have to do work. And before I do the work, I want to quickly review things about how we go back and forth between categories of factorization systems and double categories. So Miroslav has shown us that if I take categories with a strict factorization system, then I can get, well, we have a codomain discrete double category, but since we are changing the arrows around, we get a domain discrete one. I'm calling it S today just because I had too many D's in my story already. Miroslav put the D. And coming back is with corners. And we are using the corners too. And we are using G, or sorry, not G, G is corners. We are using E for the other direction, but E is not S. Just warning, because for E we have taken the subjects instead of the objects. And so, well, the two do like to talk to each other, and we're going to use that. And and in particular, because we're using the same corners to come back, if I start out with a category with an orthogonal factorization system, I go over and I come back, then I come back with a strict factorization system. And we know that because it's the one that Julia put on board, which was the one with identities, well actually no, she put isomorphism there. If you put identities in the horizontal direction, so if you take for the one class horizontal and equality, and for the other class identity and vertical, then you get a strict factorization system back, which sits inside your original orthogonal factorization system. So, and I will use that. So that is the calculation. Good. Just a reminder, if you don't know what covering flat is, so a map between Grothendieck sites is covering flat. Whenever I take a finite diagram for the first one, for the domain, and I then take the composite to get the diagram in the codomain, and I take the covering in the codomain, that covering might not factor through any images of cones in the domain, but what I'm asking for is that for that cone that I have here, that I can find a covering of arrows into the vertex so that each one of the composites does factor through a cone from the domain. And so, two questions when I want to move that to double categorical sites. First is, what should my cones be? Those are what we can call HV cones. And the second thing is, what should the indexing double categories be? Because I need to somehow know what finite means here. Here. So first HV cones, it's just that the components of my cone are not going to be just a single arrow, but they can be these corners of a horizontal arrow followed by a vertical arrow. And to be a cone over a diagram means that for every horizontal arrow in the diagram, I need to have that if I take that arrow and I restrict it to the vertical part of the cone arrow, then that's composed with the horizontal part to give me the horizontal part of the other one. And for the vertical part, we just require that the horizontal parts of so for any vertical arrow in the diagram, I ask that the horizontal parts of those two objects I now find are the same. And then okay, so what is covering flat morphism now? So I just took the old slide and I turned everything from Grothendieck to Erisman. But so the one thing I don't know yet is what is my suitable finite diagram. Other than that, it just becomes every HV cone over f after d needs to have a covering family, i.e. needs to have a covering family of vertical arrows, but pre-composed with a horizontal arrow potentially, so that the composites will factor through f images of the HV cone in the domain. Okay? So now to get the correct finite diagrams, I'm going to go back and see what's happening at the Grothendieck part. Because the definition asks for all finite diagrams, but my claim is you don't need them all. You can restrict yourself to suitable finite diagrams, the ones that I like. So first we'll have cancellative sites. I can just take the factorization that we know for functors to go for the first functor to be bijective from objects and full on arrows, and the second one to be faithful. And in that case, the cones over D are exactly the same as the cones over D tilde, because we haven't changed the objects. So we still have the same arrows, and the fact that diagrams mute it can still be checked with these guys. You don't need the extra arrows that I might have had in I. And so that's the same. And so I could actually assume that that the diagram was left cancellative itself. And in particular, just to kind of look ahead, we can even assume that I tilde has a factorization system if I just assume if I choose a particular representative for each object in my tilde. Then I have a strict factorization system there, which I will need in a moment. Okay, what do I do for CM sites? I have to do more work here. This one was more fun. Because none of our normal factorization systems on CAD are doing it for you, so we have to create something ourselves. And what we did is the following. So if I have a category A with an orthogonal factorization system or a strict factorization system, either way is fine, and I have that the right class is monic, and I define a diagram D, then I can factor this through a category I tilde, where I tilde has a strict factorization system, LR, and J is going to be injected from object, so I tilde gets extra objects for me. D tilde of L goes into E, D tilde of R goes into M, so I map into the factorization system. The cones over D can be uniquely extended to cones over D tilde. So the cones are still in one-to-one correspondence, it's just not exactly the same cone. And I tilde means finite. It's important to put extra objects in there, but they're still finite. And I am not going to go completely through that thing, I think, no. So to say a little bit how we create I tilde. I tilde is made by taking the objects of I and adding an extra object for each arrow in I. And so I'm just going to freely generate that left-right factorization system. So none of the old arrows get to play at all here. They only induce the new arrows. So the old arrow becomes an LF and an RF. Take F out. I mean, you compose to F, but it's not going to show up in any factorization system. And for any composite of two arrows, we have a lambda GF and a rho GF connecting those new objects. And all the L's and the lambdas are going to form the left class, all the R's and the rho's are going to form the right class. And the conditions of so the category we make is freely generated by the L's, the F's, the lambdas, and the R, those subject to the making these diagrams. This is actually a nice, what do you call it again, confluence system here to show that there's nothing happening here that you wouldn't want to happen. So this remains finite. This is a normal form for these things. And my claim is now that if I take Middleslav's construction for a double category and apply it to I tilde, so I tilde has not a factorization system, or actually it has a strict one, sorry. So I can make a double category out of that by this system. Then I can just take diagrams that are indexed by those double categories. And so those are domain discrete finite double categories. And to show you how that works, so if I have an F between two Arizona sites, generalized Arizona sites, and it's covering flat, I'll show that the Grothendieck corresponding arrow is covering flat, so I take the diagram into G of PTP with my strict factorization system here of horizontal and vertical arrows. Then I know that I can take I tilde, the good one, and then I can take the adjunct double functor from S of I tilde into P and connect goes to F. F was covering flat, so I can play the game with the HP cones, but if I translate that back, those are precisely corresponding to regular cones on the Grothendieck part. So I do get that if F is covering flat, GF is that. And if I go the other way, I need to be slightly more careful. So I start the diagram on the Arizona sites. I would like to take the adjunct, and this morning, early morning, I thought it was an adjunct, and it should be. The only problem is that this guy is not sitting in the right place to apply G, so I need to So we have to do a little bit of work to get to the right place. So basically, choose the representative for your objects, then the representatives for the arrows become unique, and so we end up from a diagram like this to something that feels like the adjunct, and we can play the same game again, but the cones here become H3 cones on the other side. And so we now know that, at least I've sketched here, that for generalized Ehresmann sites we can define covering flatness in terms of H3 cones over diagrams with a finite double category for which the source is a discrete vibration. We might be able to go smaller, but at least this is what we prove right now. I personally would like it if they could just be ordered categories again, but I haven't been able to get that small yet. So we have now alpha junctions. Oh, oops, not that one. Hey, wait. How did that happen? Okay. We have all these junctions. Now the next thing is, of course, to do the comparison lemma conditions. We have done them. There's nothing. Everything is going the way you would expect it. I will let you guys read those slides at your own leisure at another time. And I just want to say here that we have the categories of fractions this way. Also for Dalhousie, we can write that one down. Number 2 here is actually part of the next slide on work in progress. And not correct in they are stated here. Sorry about that. So let me just talk about number 2 for a moment, because this also talks about why do we want this. So why do we want this? Point 1, to help people in semi-group theory and kind of extend their results there. But another reason, oops, well, we may stop this here for a second. Here first this one. If I have a factorization system on the category, then Mack and Street tell us in their second paper on formal theory of monads that I get a read product. Now, the read product doesn't come in the way I wrote it here, because I need to take isoclasses on the M part. And so, it's suspiciously looking like taking the subobjects in the Ehresmann sites. And so this is something that's still, the complete connections to why this exactly works is still something that we are working on. I just learned about this last week from David just now, so we're still working that out. So in any case, in answer to our earlier question about how is appropriate topos related to an atom and atomic topos, this says that it's a weak product, because even if I take the S, the components, then that's an atom do. And the E gives me an atomic topos. So we do have every topos as a weak product there. My next question is, how far can we do this on sites? So does this work just on the whole thing, or does it also work on individual sites? And so when I take a site and I turn it into a generalized Ehresmann site, the next thing is that the double categorical picture kind of makes me do things such as take the horizontal category, take the vertical category, and I get an atomic site, I get a left-sensitive site sitting inside this guy. I also can take fractions, and I get another atomic site and another Ehresmann site, another set here, atom du. So we have another atom du, another atomic site, and the question is, what does this exactly mean? In the sense, is this invariant on the lemma comparison maps? And what are these morphisms, geometric morphisms? And what we have just worked out will help us to answer those questions, but we just haven't done it yet. Thank you.
Thank you for the talk. Questions, remarks?
We haven't looked into that, partially because we didn't have to, so to say. We were getting the speed of correlations. I'm thinking in terms of other work that I've been part of, that I can say about the correlations. Not right away. It might lead to some other representations, so we haven't done that.
It seems like you worked hard on more properties than would strictly be necessary, in the sense that covering flat morphisms is what is typically called morphisms of sites, and then preserving morphisms typically give comorphisms of sites. So is there a reason that you really worked hard to get both characterized, with one or other of those not been enough to get the result that you were after? Because I'm pretty sure that you can recover all of the geometric morphisms using either one or the other.
That's a good question. I have not thought about that. I've been used to doing both. I must say this is also my first time of really playing with sites, because I have usually worked with the groupoid representations. So I don't know, Julia, do you know?
Can you cover examples for the left examples?
I think so.
Yeah, so the morphisms of sites, the function reduces the left adjoint. With the comorphisms of sites, it's the adjoint to the induced functor that gives you that universal. So you need both when you're having something that you expect to be a morphism that satisfies the properties of the comparison element, but to generate general geometric morphisms.
So if you want to do fractions, then you do need that, I think, still both.
We can discuss that.
Yeah, okay, let's do that. Yeah, no, and I'm interested in the cofunctor aspect actually, because I suspect that that's going to help me understand better what's going on with the groupoids on the geometric side. So, let's talk more. Thank you for asking.
The formal construction of the factorization system reminded me of something that looked like the factorization that tried having stable homotopy. Is there any relationship?
That's a question for Julia.
It's a very interesting question.
No, that's what I'm really interested to know. Yeah. Because Julia had done the factorization system for sites,
yes.
And so we can look into that, because it might also help us further.
Thank you.
Thank you.
Further questions? Short one.
Unlike to my previous one, marathon sites involve double categories.
Yes.
Is there a way to get to opposites from more general double categories?
Well, that is the other reason why I want to do this. So I was like, I would like to get to maybe something like a double topos, and then this should at least be a special case. So we were like, well, let's first understand this one at the generality of Grothendieck topoi to get them to the next one, over which I suspect we will have to generalize the sets to like span of set or row function or something like that to get the more general double topoi. And then of course we might want to put more on our horizontal arrows too. We may have two topologies interacting.
Okay, so let's start the speaker again.